So again, back to the Big Bang, a lot of people say, okay, what happened before? So we kind of address this issue of time, as in maybe our understanding of time doesn't allow us to understand how there couldn't be time before.
Yeah.
But there's something else you talk about in this book, which is this concept, I think, of repulsive gravity. And
Yes.
how, again, I think the other thing people struggle with is how could something start from a pin size or nothing size and then become everything we have?
Yeah.
How do you talk to people about that?
Well, it is a hard idea to imagine something smaller than an atom in a fraction of a second swelling larger than the observable universe. I mean, that's such an incredible scale of growth that it's just unfamiliar in any realm of experience, of human experience. But when we look at the mathematics, we do find this bizarre sounding idea of anti-gravity, repulsive gravity. You and I are used to attractive gravity. You drop something, it falls toward the earth because the earth and the object attract each other. And we have never experienced any other kind of gravity. But the math of Einstein's theory shows that in certain exotic situations, gravity can be outward pushing, not inward pulling. And the exotic situation is just a region that's uniformly filled with energy. We're used to the gravity of a clumpy rock like the Earth or a clumpy star like the sun. It's not uniform. It's there and then there's empty space around it. That yields attractive gravity. But the math shows if the energy is spread out, there's an outward gravitational push. And we believe that in the very earliest moments of the universe, a little tiny patch of space was filled with this uniform energy that gave rise to a powerful outward push that drove everything to swell enormously from, as we were saying, a tiny size to bigger than all that we can see.
Wow. All right. And then now 13 billion years later, we're where we're at today.
Yeah.
And where are we? You know, if you're trying to put that in perspective
Yeah.
with a normal human, like what's been happening since and before that, and what's going to happen? Because you talk about trying to get this whole concept of time.
Yeah, to get the whole picture is a hard one. And I use an analogy in the book. I make an analogy to the Empire State Building. And I ask the reader to imagine that each floor of the Empire State Building represents a duration of time 10 times that of the previous floor. So imagine ground floor, 1 year since the Big Bang. First floor, 10 years since the Big Bang. Second, 100 years, and so forth. And so in that way of thinking about things, everything from the Big Bang until today takes us to floor 10 of the Empire State Building. And then I walk the reader from floor 10 exponentially far into the future as we walk up each and every floor of the Empire State Building. And there are key things that happen along the way. With the final, at the very peak of the Empire State Building, the universe is just left with a bath of particles floating through the darkness. All structure has disintegrated. That's entropy, second law of thermodynamics. Everything ultimately falls apart. Entropy finally wins that battle. And there's nothing but particles and the void in the very far future.